Okay, more of the same, but from a different point of view. Life and Times of JRoot was already mentioned, and previous talk about work Peter and Randy did also. When we saw this at the RIPE NCC, we saw that there's actually a little bit less stability than we had expected. And why did we have expectations? Well, when we deployed Anycast, we also had a monitoring project on which is called DNS Mon, and we had sort of cursorily looked at the data, not done really real analysis like Peter has done, but just looked at it for some intuitive results, and we didn't see that many switches. So those two studies actually caused us to roll back, look at this data, and see why there was this difference. For those who don't know, DNS Mon, it's a monitoring system. We've got data since April 2003, and we do various queries. Among them, the most frequent ones are id.server hostname.bind, same thing as Peter did, but we do it every 60 seconds. So our resolution is not as good as the every 2-second things that they did. And obviously they're Poisson distributed so that we don't latch on to any events that happen in a regular pattern. We also less frequently we query ZOA and the software versions. You can get at the loss and delay in almost real time at this URL there, so in case you're interested. I have to say that part of that website is very slow at the moment, and I'm not the one minding it, and the people who are minding it were off today because there's a public holiday in Holland, so might be a little bit slower than usual. What you have to say about this, just about the methodology, it's intended to actually measure the DNS service. I started this when there were in 2002 a couple of posts to NANOG, among other lists, about all the root servers are down, and all of that had happened, sort of figuratively speaking, was that the person who was monitoring this from one particular place in the internet had his DSL cable disconnected, and then was claiming that all the root servers were down. So I said, well, we have to do it a bit more stringently. So we do this from about 70 places at the same time. Well, to actually look and correlate what we saw with what Peter saw and what Mark reported, I just took almost a month's worth of data from February 13th to March 9th this year, and I just choose that because it was readily available and I could copy it to my laptop. At that point we have 77 boxes and 59 ASs, and I looked at the same targets as Peter looked at, CFI, JKM, the Anycast root servers. It's about 35,000 queries per probe per host for this month, and so it's about 16 million data points. The probe locations are certainly biased because DNS Mon is run on instrumentation that is mainly deployed in Europe. There are a few in other areas, and it's also biased in another way, in the sense that most of these things are within or very close to ISP infrastructure, so they're not out in the fringes of the network. It's basically what the data set looks like. It's more for reference. I don't want to talk to it. We looked at the global results of this, and there were some 16 million queries, and we found 14,000 drops. That's basically queries that weren't answered. So there are 99.9% happy queries. And remember, it takes 2 happy packets to make a happy query, query and a response. So, and we saw much less instance of switches, only 0.02%, just about. And people interested in working on this further, I can give you an URL where you can get the whole file. This is actually the main point why I'm giving this talk, to make this point again. It's not about DNS service quality, it's about studying BGP. instance switches per se do not mean DNS service problems. And we've seen the correlations that Peter showed earlier. There's some correlation, but there's certainly not a clear sort of +1 correlation factor. If we actually look at the service at the unicast addresses, the picture is like this. We have the 99.9% happy queries from the Anycast servers, and in the same data set we have just 98.9% happy queries from the unicast servers. So there's an order of magnitude difference here. And also, no offense to anyone in the room, but what people who are not intimately familiar with DNS should note is that 98.9% is also quite nice, good enough service, because there's 13 redundant servers, and this is measuring all the 13 servers. So DNS root service is fine. This is a plot of the DNS mon that shows stacked on top of each other 13 plots over this particular period that I chose, and it shows the losses per root server, and we see that they're actually quite concentrated in one, and that happens to be a unicast server. But even if you take that data totally away, the Anycast is still twice as good, more than twice as good as unicast. So Anycast works, basically. Back to BGP. When we looked at the distribution of the switches, it wasn't so interesting. So our first impression was, this agrees with what we saw when we just looked at the data cursorily. There's a little badness, but not real ugliness or worse. And we didn't have real hope for this data set to show us the same thing that Peter and Randy saw, because our resolution is lower. But then we just lumped all the data together, and we saw the same kind of distribution that you saw in Peter's talks. This is a log scale on the x-axis for the interval between switches, and the y-axis is occurrences. And you see that there's a high number of occurrences of switches that happen closely to each other. So there must be sort of bursty activity there. And that's the point when I decided to do to actually look at BGP at the same time when we have those switches. And I found a couple of examples that actually show quite well what's going on. And I used BG Play to make some movies to show that, rather than do analysis. It's not as bad as some of the stuff that Peter showed, but I think that's because of the bias in location of our probes. They're within ISP infrastructure. Quality-conscious ISPs, let's call them that, are more likely to have probes because they're interested in quality, and it's not on the network fringes. Hello? So my example here is AS1853 to k.rootservers.net. It's one that I chose because it really illustrates this very nicely. It's not to pick on either k root servers or the AS1853. It's just one that could make a nice movie from. We see that for the whole period, for the whole month, there were actually 36 switches and 8 drops, and there were two instances of K that were serving this AS1853. One was KM6 in Amsterdam, and one was K-Links at the Links in London. And actually, the switches occurred in during 8 hours of this whole interval. So it's in only 1 point whatever percent of the time, of the total time observed. This is a data file of those things. It basically gives you time of day, the time since the last switch, and you see I grouped them a little so you can see that they're clustered. The first one happens like on February 22nd, and then sort of 500 seconds later there's one 240 seconds later, there's one 603 seconds later, there's one, and so forth. Again, remember the resolution is once, on average once a minute. And it flaps a little between 439 and 537, and then it stabilizes on links. Initially it's on M6, then it flaps a number of times over about an hour, and then it stabilizes on links. And then another 1.5 hours later, about, it goes back to M6, and then another 11 hours later, it starts flapping again, and so on, and so on. If we visualize that using BGPlay, we have the original situation. The measurement point is on the left-hand side. It's 1853, for those who can read it. That's there. And the target is there. This is where K-root lives, AS25152. And this is the original state. And what I did is I used to say BGPlay to just see what happens during this interval when all these switches happen. So hey, it switches to this path, and while actually, if you look here, this path looks like it's got one more hop. If you look up there, you will see the actual AS path, and you'll see that the S path lengths are actually the same because there's some prepending happening. The lengths are actually equivalent. Now, if we overlay the original switch data, this other file to it, we see that this is actually it happens at the same time when the switch happens. The time difference is just that we see the BGP action a little later, is that it takes some time to propagate to the probe of the routing information system that actually takes this data. And it switches back in BGP, and it also switches back in our log data. And this goes on. So the first few things that you just saw in the file of the probe data is just these two paths switching, and they closely match. You can look at the stuff on the website, and you'll see that. That was quite surprising because actually there was one BGP path. I followed this through all these 38 or so changes, and there's one BGP path change logged for every instance switch. So for this one at least, we're not missing much because of despite our lower probing frequency of once a minute. The cause of the path change is probably instability on the preferred path, and I know that now for sure because I presented this last week at RIPE, and there was someone, an engineer from the transit network, from the original one, that looked in his logs, and during the talk actually stood up and said, "Yes, I know what that was. There was a link instability at that time." So this is no effect. It's not probably. And there's actually a little packet loss, but not for each switch. We can see loss. It keeps churning, as I showed you earlier on, and I'll visualize that as well. But I haven't actually logged all of them and superimposed all of them because that's just a lot of work, and I'm lazy. So all these switches actually we see in the BGP data and in the DNS probe data. And then later on, it actually sort of goes, it goes through different routes. I'll just show you the other paths without showing you the switches. But I looked at them. Trust me, they're all reflected in the DNS probes. And if you look carefully up there and look at the path lengths, you will see that prepending, they're actually all the same. So it does this and it does that, and then it does lots of this. And I looked at some of the other things, and you could see essentially the same one, the same pattern. The reason I chose this particular one was that it was so easy to lay out, so it's easy to see. So the next question that came up to my mind is this unique to Anycast? And I found no, unicast prefixes also have lots of paths of equal length and also have instabilities. And I just chose another example out of the same time frame to show you, where we have a unicast /21, also from 1853. And around the same time when this link failure happened, this started doing very similar things. And I have to say one thing here, which obviously I forgot. If you look at this, these things, 25152 is one blob here because it's one AS. But in fact, there are many of them because this is just the whole point about Anycast. So if you look at this, you have to sort of mentally replicate this 21 this thing a couple of times, because in the underlying topology, the real path the packets take, these are different destinations. Yeah. Okay, coming back here. It's this basically shows some BGP instabilities, at least the ones that I looked at, that are not unique to Anycast. And I just have, as another example, I do 1853 to F route, and unfortunately this is not very easy to see because the colors get chosen automatically by BG play and they're not always ideal ones. But you see the sort of same pattern is there. There is actually BGP instability here, which causes this. Some questions for looking further, quite similar to what Peter said. One thing that sort of I have intuitively is that there are more possible paths to Anycast prefixes because they're actually really located in different parts of the topology. So there must be more possible AS paths. But is it really so? I didn't look at that. Is it so then derived from that Anycast prefixes show more BGP paths of equal length, so that without policy tie breaks they're equivalent, and other tie breaks have to occur, and in case of instability BGP flaps more easily? Is that true? I don't know. And another possibility, which is actually quite possible, is that this is just normal BGP churn that we just very conveniently see because we can measure it now with the DNS protocol over because we have this Anycast. Are there other factors? I don't know. But, and this is the important bit, remember this one. This is not about root service quality, it's about BGP. So please, do not go out there and say that this means that Anycast for DNS root service is unstable or broken. And as Mark has quite clearly said, this is because it's stateless UDP. It's one query packet and a response packet, and there Anycast works. I'm done. Discussion. 20 minutes. We have 20 minutes for discussion. Come on, folks.
I know you've all stared at your AS data.
Yeah.
Do we have Dean Anderson in the house?
You got one?
Hi, Tony Lee. Welcome to the wonderful world of debugging BGP. Do you have anything that you can point a finger to as to what's really broke?
No, not really. No, yeah, well, intuitively yes, but not really something I would want to defend scientifically.
Working on it, and we'll deploying boxes soon, hopefully.
The answer I can give, at least. I mean,
Yeah.
right now we just found a problem, or maybe not a problem. What we found was a an effect, and we want to see causes and things like that. But right now, all we know is that it's happening, and we have all sorts of ideas. But like I pointed out in my talk, they're rampant speculation, but make intuitive sense. So switching, and it depends on whether or not the switches track together or differently, and all sorts of things like that.
I think, but if you, well, maybe that's what you want to hear, but sort of going from rampant speculation to some other intuitive things, it's like, I think there's too many knobs are being turned, too many policy knobs are being turned without actually looking at the consequences. So this prepending stuff and making paths, trying to do policy by prepending maybe other policies that are there that are not necessarily consistent, obviously make it a tough job to have a stable routing. But that's all conjecture, of course. Mark.
Hello, I'm not Dean, but I'll play one for a moment. Actually, this isn't so much that, but I'm wondering, there's multiple ways of doing Anycast, and we've kind of looked at sort of, for the most part, sort of globally available. And there's, like, for example, F does this no export sort of thing where it's seen only within their peers. So I'm wondering if there was some work done there, if we would see a reduction to this sort of path switching, and it would be less of an issue than what we've seen through our three now reports.
So are you saying that, because we saw a pretty significant amount of path switching on all the routes. I mean, F wasn't particularly better or worse than any other, as I recall.
Well, you saw their global instance. You didn't
Yeah.
see the things that were, within their own little sort of, their own Anycast pods that are out there.
Same thing with I, that what you were seeing was a small number of servers which have global routing, whereas the vast majority of the servers are only visible within the context of the Internet Exchange and the peers directly adjacent to the Internet Exchange in any given locality. So you're seeing the same thing with I and F, and I suspect many of the others, right? So what you're seeing is a behavior that's only visible from places that aren't downstream from a peer.
Yeah.
Okay.
That's actually cursory observations I had on the DNS1 data. That's exactly what I see. To say it in one sentence is, if you see a local instance, it's more likely to be stable.
Which
But there are also the last example I showed is actually a counterexample. It's because when it when this one becomes unstable, you switch to the global, and if you have multiple globals, it can do the stuff that you just saw. Yes.
Anja Feldmann, one question that comes to mind is there's a lot of multipath routing, and with some of the tie breaking being fairly arbitrary, the question is whether some of the path switches that you're seeing are just artifacts of multipath routing within the IGP.
I don't get it.
I similarly. So
You say what we're seeing is artifacts of IGP things?
So basically, if you have some load balancer or some other kind of boxes out there that are purposely rebalancing the traffic between two different routes, and then you have some other artifact there, that might actually explain why for one UDP packet you go this way and for another that way.
right, but in that kind of thing, we would expect a different sort of distribution than what we actually saw. I mean, what we saw didn't look like the sort of distribution you would expect from that, which would be sort of a classical sort of either very deterministic or Poissonish or something. But we saw switches that had their own characteristic and switch patterns that had their own characteristic in lots of ways. So I don't deny that load balancing could be contributing to quite a bit of it, but it's pretty clear there's probably something else at work as well.
Yeah, I can say for our data, we're not likely to see these things because of the low resolution. Yeah. So for all the stuff I looked at, I definitely saw BGP events for all the switch events. So there's a strong correlation there. But I didn't do the scientific bit that Peter did on it.
Daniel?
Bill?
I think that's Daniel. It's kind of hard to see. It's so far away. My question actually did sort of crop up, I guess, with Peter's data. When I asked your cohort, Peter, earlier this year about the influence of IGP events because of the placement of your collectors, both inside an ISP where there's IGP events are visible or more visible than, say, the ripe nodes, which tend to, I think, see more BGP type events and filter those out. Can you extrapolate out IGP type of events, whether it's ISIS or OSPF or IBGP, from the eBGP or multi-hop eBGP kinds of events?
Right now, no, because we don't have, or we do have BGP, eBGP feeds from lots of these places, but we don't have the IBGP feeds or the IGP feeds, so we don't have enough sort of data to start presuming about these things. I'll tell you, we are, again, we had both rampant speculation, but it was also the subject of ongoing investigation, and that wasn't just sort of hubris. We really are. We've contacted a few of the hosts, a few of the ASs that were representative in particular ways of various types of instability that we saw, and we're essentially asking to build up, if we can build a box and they just plug it into their network so we can slurp their feeds to try and figure out exactly whether it's for this kind, it is IGP or IBGP.
Okay, so that's an interesting thing, and it will cost you lots of money if you want to come into my network to do that.
Yeah, anyone,
right. So that's why we're asking very politely and promising not to unduly expose data and be very
not
sensitive.
to misbehave intentionally.
Yes.
So this isn't a DNS thing, even though we're picking on DNS servers. It's
We're
kind
using-
it's kind of a routing thing, but we're picking on BGP because we really don't know where we're shooting at. So we're taking a convenient target.
We use DNS to measure routing effects.
And we're picking on BGP because we really don't have visibility into other routing constructs that people use.
Exactly. And so we're looking to get visibility.
It may not be BGP.
But I mean, if you want to, if people want to help with finding the IBGP site, see Peter.
Yeah, please.
Bruce Campbell. One thing that would be interesting from both studies is to find out what the so-called safe distance would be for an Anycast thing. How many hops away before you start seeing severe flapping or whatever, just in terms of deploying it.
Sort of minimum safe distance from a
Sort
Anycast
of minimum
server, is that
safe
what you're
distance,
saying? But yeah, that would be sort of
Maximum
safe distance,
safe
right?
distance,
Yeah, because that would.
But yeah,
So
intuitively, that's wishful thinking. I'm not sure you can actually go there.
Intuitively, it's maximum safety. Intuitively, if you're next to it, you're probably pretty good. After that, things get harder. But I will say that is being, yes. Yeah. I agree, that would be pretty cool.
Yeah. And my other comment is that the difference between the two data sets does seem to be geographical in terms of the European data set and the
and that's also,
US data set.
Right.
So,
and the other thing is that what we saw was that's probably why Planet Lab was seen to be more stable as well, because much like how the write points are self-selected for people being, wanting to donate their data to the community, probably caring about this kind of thing and maybe running a tighter ship or something, I don't know. But also people, Planet Lab sort of has the same self-selection issue, which makes its routing situation look much better and much more stable, I think.
Hi, Patrick Elmore Akamai. I don't know if you mentioned this in the presentation, I don't remember it. When you see a switch, did you see a change in the path length? Is there any correlation?
I didn't check that out, so I couldn't tell you.
You probably won't, since everybody peers with everybody, but it might be interesting to look at.
Okay.
Intuitively, so on the examples I looked at, it's more often than not the path lengths were the same. But it's not, I haven't counted them all, so I haven't done the rigorous thing.
On the maximum safe distance thing, obviously, yeah, it's not a deployment guideline that's like asking how old do people get or something. It's not going to be a useful personal bit of information. But it would be nice to have that as a closure to a feedback loop for the people who are deploying these so that we can see whether changes we're making are for the better or not.
Right. Yeah, because if you deploy two Anycast routes that are too close to each other, maybe you're seeing double effects. Or
no, more like
that?
if we put more work into centralization, that is fewer nodes but more robust, does that help? Or if we put more work into decentralization, that is more nodes that are closer to people, does that help more?
Right, but again, remember, I mean, this is all contingent on wanting to deploy stateful services over the Anycast, because there's not a whole lot of problems with UDP. So, but yes, that would be good to look into. All right, is that?
We're done? I think we're done.
I think we're done. Okay, cheers.